At first glance, the railway system presents a contradiction that seems impossible to ignore. Steel wheels moving over steel rails should slip easily. The contact between these two materials offers far less friction than rubber on asphalt, similar to how ice skates glide across frozen surfaces. And yet trains weighing thousands of tons accelerate, climb gradients, and stop with remarkable precision. They do this without spinning out of control, without losing grip, and without relying on the kind of complex, surface-dependent traction systems used in road vehicles. This isn't just counterintuitive. It challenges our basic understanding of how motion and friction are supposed to work. So how is this possible? How can something so heavy maintain stability on what appears to be one of the least suitable surfaces for traction? The answer lies in a combination of physics, pressure, microscopic interactions, and engineering refinement developed over more than 2 centuries. Because in railway systems, traction is not just about friction. It is about control, precision, and understanding forces at a level we rarely consider situ. To understand why train wheels don't slip, we need to look beyond what the eye can see. If you enjoy engineering explained in a clear and realistic way, leave a like, subscribe to Rail Tech World, activate the notification bell, and share your thoughts in the comments. Your support helps us continue exploring the hidden systems behind modern infrastructure. Steel on steel has a very low coefficient of friction. Under normal conditions, this would suggest limited grip and a high probability of slipping. In road vehicles, traction depends heavily on friction between rubber tires and asphalt. The entire system is designed to maximize contact and grip. But trains operate under completely different conditions. They rely on a system where friction is relatively low, yet stability and control remain extremely high. This creates a fundamental engineering paradox. How do you generate reliable traction in a system that by definition should slip? The answer begins with something that seems almost insignificant: the contact area. Contrary to what intuition suggests, the contact area between a train wheel and the rail is extremely small, often no larger than a coin. At first, this seems like a disadvantage. Less contact area should mean less grip. But in reality, the opposite happens. Because all the weight of the train is concentrated into this tiny point, the pressure becomes enormous, far greater than what is experienced in most mechanical systems. This intense pressure changes the behavior of the materials at the contact interface. Instead of simply sliding over each other, the wheel and rail begin to interact in a much more complex way. At a microscopic level, steel surfaces are far from smooth. They are filled with tiny peaks and valleys known as asperities. When 2 steel surfaces meet under extreme pressure, these microscopic irregularities deform, interlock, and even partially fuse for fractions of a second. This creates what engineers call adhesion. But this adhesion is not static. It is dynamic, constantly forming and breaking as the wheel moves. Each rotation of the wheel generates thousands of these micro-interactions, and together they create resistance to motion that behaves very differently from simple friction. This is why trains can maintain traction even with such a small contact area. Because at that scale, the interaction is not smooth sliding. It is controlled microscopic engagement. Weight is one of the most critical elements in railway traction. The heavier the train, the greater the force pressing the wheels into the rails. This increases the normal force, which directly amplifies the adhesion effect. In practical terms, more weight means more effective grip. But this must be carefully managed. Too much weight concentrated unevenly can cause excessive wear or even damage the rail. This is why locomotives are engineered to distribute weight precisely across driven axles, maximizing traction without compromising structural integrity. Interestingly, train wheels are not always in perfect static contact with the rail. A small amount of slip is not only expected, it is actually beneficial. This is known as controlled slip. During acceleration or braking, the wheel may rotate slightly faster or slower than the ideal rolling speed, but within a very narrow margin. This micro-slip allows the system to operate at peak efficiency, generating maximum traction without entering full loss of adhesion. If the slip becomes too large, that's when problems begin. And this is where modern engineering plays a critical role. Today's trains rely on highly sophisticated traction control systems. Sensors continuously monitor wheel speed, axle rotation, acceleration, and even vibration patterns. These systems can detect the earliest signs of slipping, often before it becomes noticeable. When a deviation is detected, the system reacts instantly, reducing power to specific axles, adjusting torque distribution, or modifying braking force, all in real time. In advanced systems, each axle can be controlled independently, meaning traction is optimized continuously across the entire train. This level of control transforms a naturally unstable condition into a highly stable and predictable system. Under ideal conditions, adhesion works extremely well, but the real world is far from ideal. Rain introduces a thin film of water. Oil contamination can drastically reduce friction. And one of the most challenging factors, leaves. When crushed under train wheels, leaves release organic compounds that form a slippery layer, almost like grease. This can reduce adhesion dramatically, turning rails into a near-frictionless surface. To counter this, railways use a surprisingly simple solution: sand. Sand is deployed directly onto the rail in front of the wheels, increasing friction instantly. But modern systems go even further. Some networks use high-pressure water jets or laser-based cleaning systems to remove contaminants, because maintaining adhesion is not optional. It is critical for safety. At high speeds, everything becomes more sensitive. Small instabilities can escalate rapidly. Even minor variations in contact can lead to vibrations or loss of efficiency. This is why high-speed trains require extremely precise engineering. Wheel profiles are carefully designed. Rails are maintained within tight tolerances. Suspension systems absorb irregularities and maintain consistent contact. At speeds exceeding 300 kilometers per hour, there is no margin for error. And yet, stability is maintained. Because every variable is controlled, railway engineering is a constant balance. Too much friction would increase wear, noise, and energy consumption. Too little friction would compromise traction and safety. The system is optimized to operate within a narrow window, where energy efficiency and mechanical reliability coexist. This is one of the reasons trains are among the most efficient forms of transport ever developed. Even with all these systems, loss of traction can still occur. But what matters is how quickly the system responds. When excessive slip is detected, power is reduced almost instantly, braking is recalibrated, and adhesion is restored within seconds. To passengers, this process is usually imperceptible. But behind the scenes, a complex sequence of corrections is taking place, preventing instability before it becomes dangerous. Train wheels are made from highly specialized steel alloys, engineered to withstand extreme pressure, heat, and repeated stress cycles. Over time, wheels experience wear that alters their shape. Even slight deviations can affect contact dynamics. That's why wheels are periodically reprofiled, restoring their optimal geometry. So, rails are also maintained with precision, because the interaction between wheel and rail is not just mechanical. It is a finely tuned system, where geometry, material science, and physics must align perfectly. At first glance, steel on steel may seem like the worst possible combination for traction. But in reality, it is one of the most efficient and refined systems ever engineered. Through pressure, microscopic interaction, precise geometry, and real-time control, railway systems transform a low-friction interface into a highly reliable traction mechanism, a system capable of moving thousands of tons across vast distances. Every single day, all supported by forces that operate silently at a scale we cannot see, but that define everything about how trains move.